So once again, I welcome you all for the Geotechnical Engineering Laboratory of Week 1. So why do we actually need to go through this course? See, we know that all our structures are going to lie on the ground. Okay, any structure you name it, whether it's a dam or a building or anything on this world is going to lay on this ground. Okay, so this ground is not going to be the same everywhere. Okay, it's a naturally formed material. The soil is a naturally formed material. So below the ground we are not able to see what is being present there. We have heard lot of failures, catastrophic failures that have undergone during the earthquake or even due to poor construction. Okay, so it is very important to know or to have an idea what lies below our feet. Okay, so before constructing any structure, we have to have a clear knowledge about the type of soil there, or it can be a rock, or it can be any other unforeseen fault. Okay, anything can be present. It will be surprising when we do a excavation for our foundation. We would have thought there would be no clay, but suddenly when we excavate for the ground for a foundation, there could be clay lying there. Okay, so in this geotechnical engineering laboratory we are going to see what are the basic tests that is done in the soil. See, just like we human beings, okay, we are all with the same two eyes, we are all with the same organs, like kidney and liver, brain, everything. Okay, but we are all are not we are all with the same organs, but we are all not the same. Just like this, soil is also possess materials which could be broadly classified, but their behavior is not going to be the same everywhere. Okay, so here you could see these are some uh, visible things that we see in day to day life. Okay, so when we go on a road, or there could be a building which is suffered a severe damages like these cracks. Okay, these are due to the clay soil that is present below, which is not diagnosed, or which is not treated properly. Okay, so because of the structures that is laying on the clay soil, such kind of cracks may occur. You can see these kind of undulations in a pavement. Okay, so below the soil, there could be clay. So clay is a type of soil which will absorb water. Okay, so just like a sponge, I can say. Okay, not exactly, but how sponge absorbs water, a clay soil absorbs water. When it absorbs water, it increases in its volume, so it will swell. Okay, so because of that, it will exert pressure on the above lying structure, and it causes cracks and distortions in the structure. This can cause some fatal consequences. So this is one of the structure which was improperly planned and built. So one of the structure fell off by itself, and the other structure got demolished. Okay, so this was due to the poor analysis of the soil and poor design of the foundation system. So as I said before, moving on to, I just want to give you a clear idea of the broad classification of soil. In general, soil is classified into two major types, that is coarse grain. The another one is fine grained. And we have, in coarse grain we have gravel and sand, and in fine grain we have silt and clay. So it is very important when we enter into soil mechanics, we have to know these three four names: gravel, sand, silt, and clay. Okay, of these we are very much concerned about sand and clay. We will talk much about sand and clay, where we give less importance to gravel or silt. So how did they classify this four different types of soil? It is based on the grain size. So to be more uh, clear on grain size, you can see here This is what gravel looks like. Okay, so it's a very very bigger particles, you can see with your eyes, similar to what we have in our home. I usually compare this with our rice. So your gravel will be like something, will be like a rice. So when you pour water in your rice, what happens? So the water seeps through easily. Okay, so water does not stagnate at the top. So just like that, in a gravel, if you pour water, water will flow through easily, that it has a higher permeability, that is what we say technically. Okay, so and also it will not have a particle contact, that is, they will not attract to each other because of water or even without water. Okay, so they are like individual particles. Similar to the same behavior is what exhibited by the sand also. So sand is something like our rava. Okay, something particle size similar to a rava. So it will have a smaller size, in the range of 4.75 to 75 micron. Okay, so within that we will classify as coarse sand, medium sand, fine sand. Okay, we'll see through that later, we don't doesn't bother about the numbers now. So okay, this is how similarly this is how a sand will look like. It will have a good angle of internal friction, we say, that is what gives the strength to the sand. Or so it will have better, we can consider sand as a, okay, it's a good material, it's a good material. If we have sand in our site, then it is very good to work. And also again, we have to see whether that sand is in dense condition or in a loose condition. Denser means it is tightly packed. Tightly packed means it will have a very less permeability, and it will have very good strength. Always in soil mechanics we bother about three things: one is permeability, shear strength, and settlement. Okay, these three are the engineering properties we tell. Wherever, when we go for a ground condition, we will analyze these three things: whether it has very good permeability, whether it has a very good shear strength, whether it has a less settlement. That three properties we always look after. Okay, so when it comes to sun, okay, it will exhibit all these three properties in a very good manner. Next, silt. It's like intermediate, we do doesn't have much influence. Next comes the clay. Okay, so this is like kind of a problematic always. It is one of a problematic soil, as I said, when it interacts with the water. So when there is no interaction between with soil and water, there could be no soil mechanics itself. So this clay is a chemically weathered product. Okay, so it comes from you know that from rock only we are getting the soil. By for million years it has undergone weathering. So it is a chemically weathered product, where your clay, in day to day life we have seen that clay was used in our agricultural fields. Okay, why? Because it has good moisture holding capacity, so that your plants can grow well. But in comes to foundation, when it holds moisture, it is not very good for the foundation. Okay, so it will swell and it will affect the structure. And when it shrinks, when it loses water, when it dries out, okay, it undergoes shrinkage like this. Again, because of this shrinkage also, it will cause some distress to the structure. So the swell shrink mechanism of clay is a very big issue, which need to be addressed when we are going to have it in our site. So it is something like our wheat flour. If you see wheat flour, if you mix water with the wheat flour, you can see that our in our houses it will big, we can make rolls, and we make chapatis with that. Okay, so why? Because there is a absorption capacity of the wheat flour to the water, so that only we are able to roll it. And that water itself, if we exceed it, we are not able to roll it. It will stick to the pans and the sticks, something like that. When we have it in our roads, if you're going to compact, if the water becomes more high than required, it will start sticking to the rollers, we will not able to compact the roads. Okay, so we have to be very much sure about this water content of the soil when it comes to the clay or any material. So to keep it mind in a easy manner, I said the behavior of clay will be something to similar to a wheat flour, where it gets absorb water well, and it will sticks to our plates when the water is going to be very high. So the ground below our earth is not going to be something a very uniform one. You can see it is going to be different layers of soil, as I said, it is going to be in mixtures also. Okay, it's not going to be here, it's going to be a complete clay, complete sand. It can be complete sand when we go for desert areas where there is not going to be any not going to be any clay particles. So below ground it can be a mixtures of layers, it can be mixtures of soils. So it is very much important when we to do the laboratory test and analyze the soil types in a proper manner. So this site investigation is a very basic thing where we collect the soil and bring to our labs. Then we do the laboratory testing. So site investigation they do in both offshore, as I said, even in marine structures and for onshore structures. So they collect soil even from our marine below sea, and they bring to the lab and they conduct some basic tests. These tests are like standards, they are the same everywhere. Okay, so we have to know the basics of the test, and we have to know how to analyze it properly from the results. So I always compare this soil mechanics or laboratory test similar to our medical field. So they collect samples from us. They collect our blood samples, and they do some X-rays and the CTs for us, and they diagnose what is the problem in our. So even we have blood WBCs, RBCs. So they diagnose your reports. They diagnose your reports and they see, okay, this is your issue. Your RBC is low. Your platelets is low. So similar to that, we also bring the soil, we test it in our lab, and we give a similar report. Okay, this soil has some high amount of clay, or this soil is having some issues, or it can have some sulfate contents, chemical contaminations can be there. Okay, so we also analyze. You can see this is x-ray of a person with a watch inside. Okay, so similar. So okay, there's a fault zone in your area. There could be some 10 years or 50 years ago, there could be a well, they could have put a soil filled, they could have created as some filled site. Okay, all these things we are able to find out only when we do some proper laboratory testing. And once we do the test, we give the solution. Okay, we give a medicine or surgery. Okay, similar to that, we give solution what could be done to the problematic soils. So these are the overview of some laboratory tests. I don't want to go in deep. One by one we will come to know. Okay, and these are the field tests. So not only we are going to do sample analysis in our laboratory, we have to directly do some institute test in the field, so that we will be able to correlate the both the field and lab results and arrive at a solution. So this is the overall test what we are going to see in the upcoming weeks: soil processing, specific gravity, field density, grain size analysis. So these four tests we are going to see this week. Okay, fine. I just want to see the attendance. Okay, thank you. So you are very much clear now why we have to do or why we have to test soil in our lab. Okay, so what is the importance of soil mechanics in the field of civil engineering? Okay, these are some references given by professor. Okay, so I have added some more. I will be uploading this PPT also. I have added some more references in this Gopal Ranjan book can be very much helpful to learn basics. Okay, even for gate and even for clearing my PhD in IIT Madras, I used this book. Okay, it covers basics with the reasonings. Okay, it's a very good book. And we have another one good book that we follow, so Holz and Kovacs. Okay, you can get the PDF of these books from the online itself. Okay, so the first uh, thing what we are going to find out is water content of soil. Okay, imagine, so we have brought a gunny bag of soil. For 3 to 4 gunny bags will come usually for consultancies. So they will bring the soil to the lab and they will do the soil processing. Okay, that you can go through in the video. But on a just on a lighter note, if I have to tell, okay, there are some raw soil from field they have brought out, and the soil will be spread out for air drying for 24 hours. So they will be spreading out in a uh, HTP sheets, and it will be air dried for 24 hours. Then the soil will be crushed. Okay, they will be crushed in a hammer, and we have also have a soil pulverizer, so they will be pulverized. Then they will be passing through sieve, the required sieve. For different tests we have different sieve, so generally we pass through 2 mm sieve, and we will store it in bins. Okay, so first and foremost we have to determine what is the water content, or we can call it as a water content is a general term. Okay, so any test what we do in a liquid limit or a compaction, as I said, water content is a very very important parameter for a soil. The behavior of a soil depends on the water content, the state of the soil. For example, if the state of the soil, they say it is in liquid state, in the field itself it is not in a it is in a flowing condition, that we call it as a liquid state. Okay, even inside it can exist, we call soft soil, soft clays. So water content is very very important. So how do we determine the water content? So we have to take tar empty tar or empty containers. Generally we go for 3 containers so that we can get the average. So measure the weight of the empty containers. We have W1, W2, W3. So measure what is the weight of the container. So I have measured the weight of the container is 16 grams, example 16 grams. Then put the soil in that. Okay, whatever the natural soil that is brought from the field, you can take a little amount of soil and place it in the container. Why I have mentioned it as a wet soil is, even if the field soil is going to be dry, it is not going to have a complete dry state. If, the soil have a tendency to absorb moisture from the atmosphere. Okay, that we call it as natural moisture content. NMC we call it as. Okay, natural moisture content. So the soil, even if it is not mixed with water, or even if it is not exposed, it is not exposed to rain or anything, even if it is underground, yeah, it will have a tendency to absorb moisture from the atmosphere. So that natural moisture content we need to find out. So we'll add some soil to the container, and we'll measure what is the weight. Okay, so the weight of the soil plus the container, it is going to give me some 30 grams. Now I have to place the container in a oven. The oven has to be maintained at around 105 degrees Celsius. So at that temperature, the crystalline water also will be able to be removed from the soil. So uh, the water, any water that is present in the soil will be removed. Okay, so you'll have to maintain an oven at 105 degrees Celsius, and we'll measure for 24 hours we'll be keeping. So the soil is kept in the oven for 24 hours. Now it is removed, and now you measure what is the weight of dry soil plus tar. That's going to give you around 25 grams, for example. Now calculate what is the weight of the water. So when we minus 30 minus 25, wet soil weight plus tar minus dry soil weight plus tar, these two weights if you minus, we will know how much water is present in the soil. Okay, simple calculation. Then you find out what is the dry soil weight, that is going to be, if you minus the tar weight from this 25 grams, 25 minus 16, so that is going to be a dry soil weight, or we call it as solids, dry solids, that is going to be 9 grams. So water content is nothing but ratio of weight of water divided by weight of dry soil. Weight of water divided by weight of solids we can call, or we can call weight of dry soil. So your water content is 5 by 9 into 100, it is always expressed in percentage. So 55 percentage, around 55 percentage is the water content present in the soil. Okay, so it's clear. Is anyone having doubt in this, how to find out water content? So nothing, you take a cup, put the soil in that, measure the weight, keep the cup in the oven for 24 hours, and then take the cup out and measure the weight. So you have two weights, wet weight, dry weight. So that will give you the weight of water divided by, now you have to find out what is the dry solids weight alone, which can be find out from deducting the tare weight. So the dry soil weight is going to be 9 grams here. So 5 by 9, that is going to be 55 percentage. Water content is calculated. Generally we calculate for three trials and we report the average. Fine. Next comes specific gravity. So next to water content, specific gravity. uh, See, these terminologies like specific gravity, dry unit weight, void ratio, porosity, all are these terms are like abcds in soil mechanics. We are just learning abcds in that. In future when we go to complex problems like bearing capacity or a retaining wall pressure, everywhere all these terms will come into play. That time we will know, okay, this is why we have learned, or this is how these terms are calculated. Okay, so as I said, void ratio is also one more important parameter in soil mechanics. So we'll see specific gravity. So specific gravity, there are two specific gravity, one is mass specific gravity and the other one is specific gravity of solids. Always solids, that is what we concentrate in soil mechanics. Why? Because is when you have soil, soil will have water, air in it. Okay, when you take a, just take a handful of soil, there will be solids, that is your soil particles, and you have air in between the particles, and we have absorbed water. Okay, so all the three will be there. In this, weight of air is negligible. Weight of air is not going to matter, whereas weight of water is a parameter which is changing with respect to your absorption and drying thing, whereas solids it will never change. So always the specific gravity with respect to solid is very very important. It will not change, it is a constant parameter. It is constant for a soil. And it will, for example, if you take a clay, generally the specific gravity of clay will be 2.7 in the range. Okay, 2.7 to 2.72. But for sand it is 2.65. You may think that 2.65 is nothing but closer to 2.7, but it is not actually. It creates a difference. The behavior of sand and behavior of clay itself different. Okay, so for sand it will be 2.65 around. So this specific gravity will help you in future calculations of all our other parameters. So specific gravity is a ratio of weight of solids to the weight of water. It has many different definitions, but one thing you can remember is, um, with respect to water we have to find out what is the density of your solids. That is what you can remember. Okay, with respect to, we already know what is the density of water. Okay, with respect to water we are going to find out what is the density of the solids. So we generally we use two types of equipments, or for two different soil. For example, if you are going to have finer soil like clay or silt, you have to go for density bottle method. If you are going to have larger particles, coarser fraction, we have to go for pycnometer. This bottle we call it as a pycnometer. Okay, so depending on the soil and depending upon the fines, you have to choose the equipment. So in density bottle you can see you have a small bottle and you have a cap. Okay, the method of testing is going to be the same in both the thing. Measure what is the empty weight, that is a w1. Okay, you have a density bottle with a cap, measure what is the empty weight. Fine. Next, add your soil. Add your soil to the bottle, put the cap and measure what is the weight. Approximately we can take 10 to 15 grams for a finer soil. Okay, so we can put the soil, or approximately 10 grams, and put the lid and measure the weight. So this is our w2. Then we add water. We add water up to the 3/4 level. and then we have to remove the air inside. Okay, so how do we remove the air inside? We have two ways, whether we can apply a suction or a we can place it in a desiccator, and we can apply suction, vacuum suction, so that air will be out from the soil, or we can boil it. Okay, when we boil it, you can see bubbles coming out. So that is also one visible method where you can see literally the air is coming out from your soil. Okay, so when you boil in a hot plate, air will be the entrapped air between the solids part, between the particles will be coming out. So we have to fill it 3/4, remove the lid, and we have to boil it. Then boil it for some time, and then take it, cool it down, then add water up to the rim, then close it, wipe the density bottle clean, then measure the weight. So now we have uh, the weight, that is W3, which is going to be weight of bottle plus soil plus water. Okay, so first we measure empty weight, bottle weight, then bottle plus soil, then bottle plus soil plus water. Then fourth step, remove all the contents of the bottle, wash it properly, then fill the bottle with the water, then close the lid, wipe it, and measure bottle plus water weight. Okay, so we have four weights now. Now, with these four weights, we are going to calculate what is the specific gravity. So, I have given a model calculation here. We need to measure what is the temperature we are conducting it, and also all these tests has to be conducted in using a distilled water. Okay, not with any tap water or anything. All this should be conducted with the distilled water. So weight of bottle plus soil, weight of soil plus water, then weight of bottle plus water. Okay, so we have four weights. Now specific gravity is nothing but W2 minus W1, that is the weight of dry soil we get, divided by W4 minus W1 minus W3 minus W2. It's a direct formula. Okay, so by from this formula we can get what is the specific gravity at that temperature. We have to find out the specific gravity at 27 degrees Celsius. That is what we have to report in general. Okay, so we have to do a temperature correction. uh, we have to find out what is the relative density of water at the room temp. We have a standard table, for that. Okay, so at room temperature we can find out what is the relative density of room water, and at 27 degree what is that temperature. So we have to apply that correction factor to the measured value. Okay, so this we get directly from a table because water for it is established. So this at 27 degrees Celsius we have to report. That is our first main thing we have to keep it in mind. Okay. Okay, so just to give a rough idea. Okay, so this here I have put a pic. So the specific gravity, you can see that it is measured in same containers. The ratio, we are measuring the same containers. Here it is filled with soil, here it is filled with water. Okay, so with respect to equivalent volume of water, you are going to find out what is the soil weight also. Okay, so that so, as I said, density, since the volume is same, it will get cancelled, and with the weight itself you are finding out what is the specific gravity. Many books would have put gamma s by gamma w, that is unit weight of soil by unit weight of water. Since the volume is same in both denominator and numerator, that volume gets cancelled, and from the weight measurement we are able to measure, or we are able to get the specific gravity. So this is the specific gravity of solids. We have to use oven dried soil for the specific gravity. That is one important thing. Uh, in our IS code, we can see that there is a table for which type of test, what type of soil has to be used, whether it should be air dried or it should be oven dried. Okay, so for specific gravity, we have to use a oven dried soil. The same method will be followed for a pycnometer. So this pycnometer will have a small conical shape here, so that we can remove the air from that. You no need to boil or do anything. Since it's a larger particles, picnometer is for coarser fraction. Since it's for larger particles, the air gets easily removed from the soil. So you have a small hole. Up to that hole we have to fill it with water, and we'll be following the same procedure as mentioned before. So as I said, there are two specific gravities. Okay, one is going to be the specific gravity of soil solids, and the another one is called as mass specific gravity, where you are going to consider the entire mass of soil including water, everything. Okay, like you can see here, gamma s by gamma w. Gamma s is the unit weight of solids, whereas gamma is going to be the unit weight of soil as a whole. Okay, this, if you see here, this is constant. So that's why in all calculations of all property determinations of soil mechanics, they always use only this specific gravity, that is solids. This is nowhere used. Okay, this is just to for a knowledge purpose, we are finding this out. There is a small model problem. The mass specific gravity of a fully saturated specimen of clay has a water content of 30.5%, is 1.96. So the mass specific gravity, as I said, as a whole, uh, soil as a full, they are finding out one is going to be 1.96. The water content is 30.5 percentage. Oven on oven drying, the mass specific gravity is 1.6. Now they are asking what is the specific gravity of clay, that was your solids. What is the specific gravity of solids? There's a similar problem like this in your assignment. Okay, so they have given it is a saturated clay. Soil can exist in three state. One is fully saturated, that is where all the voids are filled with water. Okay, it is like you are immersing soil in a water, deeply immersed. All the voids is nothing but, if you see, this is one soil particle and this is one soil particle. If they come in contact, you can see a small uh, hole created. Okay, so this is what we call it as void. At the point of contact, you are going to have voids. Okay, so even you can take one uh, rice grain and another rice grain, just keep it in contact, you'll have voids between the particles. Okay, so if the voids are completely filled with water, we call that as fully saturated. Okay, when your soil is completely dry, okay, if it is completely dry, all the voids will have only air, there is no water, so we call that as dried soil. Whereas partially saturated means in a full mass of soil, some voids are with water and some other voids are with air. Okay, so it is not completely saturated, or it is not, neither it is saturated nor in its dried state. Okay, some voids will have water, some voids will have air, we call that as partially saturated. Okay, so for a saturated clay, so that means that the soil is fully saturated, all the voids are with water. Mass specific gravity is 1.96. So the mass specific gravity here denoted by gamma bulk by gamma w, which is also equal to gamma saturated by gamma w. Okay, so unit weight of water, gamma w, this is the unit weight of saturated soil. So 1.96 equal to gamma sat by gamma w, that is what given. Okay, so gamma saturated equal to g plus e by 1 plus e into gamma w. It's a formula. There are some basic formulas for soil mechanics, okay, which I will also share in this presentation. You please try to memorize certain formulas, whereas certain formulas can be derived. Okay, not to memorize all, just with the three or four basic formulas you can derive the other formula. So it is gamma saturated is g plus e by 1 plus e into gamma w. So what is this e? It is void ratio. We call that as void ratio, which is nothing but volume of voids to the volume of solid. That is how much how much voids are present in this much of solids. That is what a measure. It's not directly someone is going to take a scale and measure. Okay, it is a quantity which is to be derived from other ways. Okay, so void ratio uh, is given by E, G plus E by 1 plus E into gamma W. So in this, we take this gamma W to the denominator. So gamma sat by gamma W is G plus E by 1 plus E. We know that gamma sat by gamma W is 1.96. Okay. Now at saturation your degree of saturation is 1. They have given water content equal to 0.305. So there is one more formula, that is SRE. We call the degree of saturation as SR, S suffix R, or we can give as S, SE into WG. So this is one more formula. So S is 1 because at degree of saturation, saturated soil, S as 1. Dried soil means, can anyone tell what is S? What could be the value of S for a dried soil? See, degree of saturation is nothing but degree of saturation, yes, nothing but volume of water to the volume of voids. That is, in this much volume of voids, this much volume of water is present. This much volume of voids, this much volume of water is present. That is what degree of saturation. Now, for a dried soil, what is the value of S? Did anyone text? Zero. Very good. So you are very now into the soil mechanics correctly. So this is very easy to remember. Okay. So when the soil is dry, your volume of water is going to be zero. So S is going to be zero for a dry soil. When it is saturated, these are some hidden things where they won't tell you explicitly in a gate or anywhere. Okay. So you have to understand, for a soil is fully saturated means you have to take the degree of saturation as 1. Okay, in percentage, okay, it is 100 percentage. We when we substitute, we put it as 1. Okay, fine, thank you. So where were we? So SRE equal to WG is a very important formula. Okay, many questions this formula will come. SRE equal to WG. W is your water content, G is your specific gravity, that is GS, specific gravity of solids. So now from here we get E equal to 0.305 times G. Okay. Now you substitute this 1.9. Now we have G plus E by 1 plus C, where we need to find G. We have E also in terms of G. So when you substitute, everything is in terms of G. So only unknown is going to be your G. So by solving the equation, you will be able to get the specific gravity. So what I did, so the mass specific gravity is nothing but gamma sat by gamma W. That is a formula. Gamma saturated by gamma W. So gamma saturated formula is G plus E by 1 plus E gamma W. So in this, I brought this gamma W to the bottom. So gamma sat by gamma W value I know. One is which is going to be 1.96. So 1.96 is G plus E by 1 plus E. Now I need to find out what is the void ratio. So SRE equal to WG. So in this, S is 1, water content is given. So 0.305 times G. So when I substitute 0.305 times G here, everything is in terms of G. So now I get what is the specific gravity of solid. That is what we need actually. Okay, fine. So is anyone having a doubt in this problem? Because a similar problem is there in your assignment also, where you have to use these formulas and solve the equation and find out. Okay, nothing complex in that. So here you can see an oven drying weight they have given. It is of no use. So these are just to give you some misleading confusion why they have given this data is of no use. Okay, so no need the oven dried mass specific gravity value. Fine. So first we have seen about water content. Next we have seen about specific gravity. Okay, now we go for field density test. Okay. So you have seen construction of roads, especially they use this compacting rollers, okay, which will be running to and fro, and it will compact the ground. Okay, so how do you know that it is compacted? Compaction is a process in soil mechanics where you reduce the voids. Uh, to be in simpler fashion, I can tell. We see that our homes at our homes they used to fill this Horlicks or Boost anything. Okay, when they fill the Horlicks, they used to tap it. Okay, they tap on the ground. Why do they do that? Why do they tap it? Yeah, please. I'm just asking a general question. What we do at our home? Why do we tap it? Tap the container? Anyone can answer. I don't know who's there. Your faces or your names even. Anyone can answer. I just looking at the screen only. Yeah. When we fill any material like a Horlicks or Boost, okay, in a container, after filling some three-fourth, okay, they used to tap it. Tap the container before filling it to the fullest. Why is that? So that you get more space. Okay, so what's happening is you are actually vibrating it. Okay, so the particles will come to a more denser fashion. Now you will be able to fill more. Okay, when you fill it to the densest packing, you won't be able to insert the spoon inside. It will be little bit difficult to insert the spoon and close it. Okay, so why? Because when it is in densest condition, the voids are less, so its strength is more. Okay, so you'll be finding difficult to insert a spoon. Similar fashion, they compact the soil to the densest with the road rollers. Okay, then they spray water, because water is acting like a friend now. Okay, so up to a certain limit, when it is going to be up at a particular limit, it will help you to attain a maximum density. So it will help to slide the particles, and it will help the particles to come to a more closer fashion. Excuse me. But if the water is in more, when it exceeds a particular limit only, it is going to cause a issue. Okay, they have compacted the road. Now how do we know what is the density it has attained, whether it is under compacted or over compacted than required? So we have to do a field density test. Okay, and also when we need to know, when we have our shallow foundation or something, when we need to know what could be the in situ density where your foundation is going to rest. Okay, you are going to rest your foundation on a natural soil. So what is the in situ density of the soil? Then we have to do a field density test. So field density test is done by two major ways. One is going to be sand replacement, the another one is going to be core cutter. That is the most broad methods followed. Okay, we are going to find out what could be the field density. So here what they are for doing is a sand replacement method. Okay, so this is a tray and this is sand pouring cylinder. I'll just come into that deeper. Okay, so they are finding out the field density of the ground. Okay, first we'll look into core cutter method. Core cutter method is useful only when you are going to have a cohesive soil and the soil has some moisture content. Okay, then only you can do a core cutter method. When I demonstrate the procedure, you will understand why it is suitable only for a cohesive soil. Cohesive soil is nothing but, in general we call that as clay soil. Cohesive is cohesion is a force of attraction. Okay, so between the particles, that we call it as cohesive soil. Cohesion less means sand or gravel. As I said, particle and particle will not attract to each other, but clay particle, you know that they stick to each other. So for clay soil we use a core cutter method where we have a hammer more dolly. This is the dolly and this is the cutter. Okay, so the cutter will have a sharp edge at the bottom and it is of standard dimensions. So what we do is we place the cutter and the dolly or collar at the top. Okay, this is your ground, plain ground. Just simply clean the place, clean the strata and the place the cutter and the dolly, then hit with the rammer. So this rammer will be hit on the collar. Okay, so this will penetrate into the ground, this will penetrate into the ground as you can see, till this collar is about some 1.5 mm above the ground. 1.5, correct, 1.5 or 1 mm above the ground we have to hit it. Okay, then we have to remove the surrounding soil, we have to remove the surrounding soil carefully. Then we have to remove this dolly and cutter together. Okay, so finally you will have a soil that is be inside your cutter. Now if you are going to have, imagine if you are going to have a sandy soil in the strata, you cannot do that. Your sand will come out through this cutter. Okay, the top and bottom is a hollow. Okay, so when you hit with your rammer, the soil will penetrate into this and you'll have a uh, cohesive soil which can be held in this cutter. Okay, so what are the parameters you measure? You measure what is the height of the cutter without the collar. Okay, I'm not talking about the collar now. You have to measure only the cutter height. You have to measure what is the internal diameter, then you find out what is the volume. Now you know what is the weight, empty weight of the cutter. Then you find out what is the weight of cutter and soil you have taken from the field. Bring to the lab and find out what is the weight of cutter and soil. Then you measure what is the weight of the soil. How do we get? We can detect the weight of the cutter, so that we measure what is the weight of the soil. Then we find what is the wet density. Okay, so we call this wet density or a bulk density. Okay, so it is like a partially saturated, it is not, when it is not fully saturated, it is not dry, so we call that as a bulk density in general. Okay, so your bulk density is your weight divided by the volume of your cutter, that will give you the wet density. So by this method we can find out what is the wet density. You have to take a sample of soil and you have to keep it for water content. So how do you measure water content? How do you measure water content? What is the formula? Weight of wet soil minus weight of dry soil divided by weight of dry soil. Okay, into 100. So you find out what is the moisture content or water content. Then you find out what is the dry density of the soil. How do you find dry density? That is a formula we have, gamma d equal to gamma b by 1 plus water content. Yeah, thank you. So this is how we find out the dry density. From dry density we can get one more important parameter. What is that? You can get your void ratio, very very important parameter for a soil. So from dry density, if you know what is the specific gravity of the soil, you can know what is the void ratio of that soil, and then you get the porosity. Okay, so in general, lesser the void ratio, I can compare some two soils like this. Okay, I have a void ratio of zero point 0.6 and I have a void ratio of 1.1. Can you tell me which soil will have higher permeability? I have two soil. I have two strata. Okay, strata, they have void ratio is zero point 0.6 and in another so which have high permeability 1.1. Thank you. So higher the void ratio, higher the permeability. Okay, so see, we can correlate our index properties with the engineering property. That's why it is important. So since the void ratio is very high, you can come to a conclusion that okay, that area will have a high permeability. Okay, it can have a lesser strength also. Okay, such things. Okay, fine. Now the next method to find out the field density is sand replacement method. So I said when you're going to have a cohesionless soil, or when you're going to have a dry strata, or whether the strata will have lot of bigger particles like bigger stones and all, where you cannot drive your core cutter smoothly. It is not possible to cut out the sample just like and retain it in that. Okay, so it is, the other option is going to be your sand replacement method. So in a sand replacement method, we have two things, two stages. One is going to be the calibration of can, and the other one is going to be in the field. Okay, so you have three equipments. One is going to be your calibration can, sand pouring cylinder, and this is a tray. Which this sand pouring cylinder, sorry, this calibration can will have 10 centimeter dia and 15 centimeter height, the standard dimension, and this is going to be 10 centimeter in dia, this tray. So you are going to find out the field density from a standard sand. Okay, so we have a standard sand of you like Ennur sand or white. Yes, do anyone want to say something? Okay, so we have some standard sand where we will be using that, uh, and we calibrate the scan, and we will find out what could be the density of that sand, and using that we are going to find out what could be the density of the soil in the field. So what we are going to do first is, you fill the sand in the sand pouring cylinder up to certain height. Okay, up to certain height means like till the below some like 3/4, more than 3/4. Okay, it's up to us only. Okay, so you fill the sand in the sand pouring cylinder, and measure the weight of the cylinder and the sand. Then you place it on the calibrating can. You call this as a calibrating can. You place this cylinder on the can, and you open this shutter. We call this as opening the shutter. So once you open this shutter, the sand will flow freely into this. And once you see, when there is no movement of the sand grains, you close the shutter, close it, remove it. You can see that this is the way the sand will be filled. Why? Because you have a conical portion here. Uh, this conical portion will be formed at the top. Then you measure what is the weight of the cylinder. Okay. Now again, you place a cylinder on the plain flat ground, and you open the shutter, and you see, uh, when you see when there is no movement of grains, you can close the shutter and you remove it. So you can see that this conical heap has formed on the plain ground. Then you measure what is the weight. So why we want to do this, why we want to make our cylinder like a cone has to be formed? Can anyone tell why this cone is being formed, and why we are then detecting, you will be detecting this cone weight? See gen Yeah, that's correct. uh, why do we need, imagine without this conical portion, the cylinder is having a flat bottom. The If you see, the cylinder itself has a conical portion inside. Okay, imagine there is no conical portion inside the cylinder. There is a flat bottom. What will happen then? See, the tendency of sand, you just take sand and pour it in the ground. What is the shape it makes? It makes a triangle. Okay, so when you pour sand, it makes a triangle. It will have, we call that as an angle of repose. That is, the sides of the triangle will be forming a particular angle. When you keep on pouring it, after forming a particular angle of triangle, the sand particle will start rolling on the sides. Okay, so it's like a constant, that a triangle which is formed, it will have a constant angle that we call it as angle of repose. So if there is no conical portion inside this cylinder, if there is no conical portion, the triangle will be being formed from the inside of the can, and the triangle will be at the top. So you'll have some gaps inside the can. The motto of this, see, what is density? What is density actually? Weight by volume. You are finding the density of sand. You know what is the weight of sand? You want to know what is the weight of sand filling this volume of container. Volume, okay, you are calculating by knowing the measurements. Then you are finding what is the weight of sand required to fill this volume. If that volume is being filled with a cone inside, then it will not be a proper volume. Now if you see, when you minus this cone, you just minusing, you are detecting, subtracting this cone weight, what exactly you are getting? You are getting exactly the sand that is filling the can. Okay, so that's why this conical portion is being provided in the cylinder. So that the cone being formed inside the cylinder will be avoided, and we get exactly how much sand is being filled in this cone. So I have given a calculation. See, this is the weight of sand in your, one second. Okay, so you are finding what is the weight of sand in the cone. Okay, what your volume of the container, weight of sand plus cylinder before pouring the, that is before opening the shutter, then mean weight of sand plus cylinder after pouring. So first you measure what is the weight of the cylinder before pouring into the container, then you measure what is the weight after pouring, then measure what is the weight after forming this heap. When you minus these weights, you will know what is the exact weight of the sand in this container. So that weight divided by volume will give you the density of sand. So now we have the density of sand, which will help you in your second stage. So in the field, you have to place this tray. Okay, you have to fix the tray so that it's not moving. You have to make a hole, you have to dig a hole. That hole should be of 10 centimeter dia, because you are making that hole using this tray, and height should be exactly 15 centimeter. Okay, similar to your calibrating can. So make a hole of 15 centimeter height and 10 centimeter dia. Now you have to fill the cone to the initial level. Okay, up to more than 3/4. Measure the weight. Okay, after filling the cylinder, measure the weight. Then you place the cylinder exactly on the top of the hole, and you remove the shutter or open the shutter. One thing is, when you're excavating the soil, you have to carefully place this excavated soil inside the tray. You should not throw the soil away. So you have to place the soil in this tray. Now you open the shutter after placing the cylinder. Now you see the particles moving inside your hole. Then you close the shutter when there is no particle movement. Then measure the weight. You can see in the ground a heap has formed above, and there is going to be the sand being filled in the hole. Now you have to find out what is the weight of soil that is in the hole that you have digged and taken and placed in the tray. Na? This weight, this soil weight, you have to find out. Then you measure what is the weight of sand plus cylinder after pouring and before pouring. That weight you have to note down. Then you find what is the weight of sand in the hole. So from minusing these two weights and the cone weight that we took in previous stage. See, W1 is this weight 11,000 minus After pouring is 8,000. Okay, W2 is this cone weight here, 450. Okay, so that cone weight will be detected, and you will know how much exact soil is present in the hole. So you will get 1750. Then you find what is the bulk density of the field soil. How do you find bulk density of the field soil? You can see here, this is a direct derivation from this only it has come. Okay, so you know what is the weight of wet soil. As I said, you know what is the gamma sand that you have found out from the previous stage. Now you know what is the volume of pit, that is weight of sand by gamma of sand. Weight of sand, you know, 2135, and gamma of sand, that is what we found out, that will give you the volume of pit. Now the density of soil is weight by volume. Weight of soil again 2532, that is going to be your wet soil collected divided by the volume, that will give us the bulk density of the soil. I'll repeat once again. You know what is the gamma of sand, that is from the previous stage. We know what is the density, that's what we do in the calibration stage. We find what is the volume of pit. So our volume of pit is the weight of sand that is filling the hole divided by the density of sand. So we know how much volume of the pit now. Now, in this stage, we know what is the weight of soil that we have collected. So the weight of soil by volume of pit will give you the density of the soil. So from the density, we can find out what could be the dry density, what could be the void ratio, same like previous stage. Is anyone having doubt in this field density test? Any doubt? Anything you can ask me freely. Any doubt or confusion? See, in the first stage, we are finding the density of sand. Okay, we know the volume of can, weight of sand that is filling the can. In the second stage, we don't know the exact volume of the pit, because it is going to be uneven ground. Okay, even though we dig it for 10 centimeter height and 15 centimeter thing, it is not going to give you the exact volume as our can. So we need to find the volume of that hole in the ground. So we are finding the density of sand in the lab. We are filling that sand in that hole, and we are finding what could be the volume of that hole. Once we know what is the volume of that hole, we already know how much weight of soil we have excavated, and from that we find what is the density. That is the concept. Okay. So just an overall picture. So you see that inside it will be a heap formation. So this is your can. You open the shutter, fill the can, and you open the shutter and fill the on a level surface, and fill the cone. Then in the hole, you dig a in the ground, you dig a hole, and you fill the hole. These are the three things: on a plain surface, on the can, on the hole. Three things. The weights you have to take every time after filling. Okay. So this is just a model calculation. So you are finding the dry density. You are finding, once you know the specific gravity, you know what could be the void ratio, what could be the porosity, and even degree of saturation. SRE equal to WG. They have used M. It's up to you. Once when you are going to follow one notation, keep it same for all your throughout your practice. Okay, so M is nothing but water content. So SRE equal to WG. So you know what could be the degree of saturation at the ground. So as I said, these are some important formula in soil mechanics. I have just put a box for a very important formula. From this you can derive the other formula also. So gamma bulk, that is your gamma bulk equal to G plus SC by 1 plus C into gamma W, and your gamma dry unit weight is G gamma W by 1 plus C, and SRE equal to WG. Porosity, N equal to E by 1 plus E. Water content is weight of water by weight of solids. These are very important formula. Like any competitive exam question paper, or any gate or any paper you take, there will be sure one question from index properties that will be relating any of these formulae. Okay, if you know what is a bulk unit weight formula, you can actually derive your gamma d and gamma sat. The derivations are available in the book, please you can refer. You no need to by heart all the formula. If you know to derive, you can easily get it. Okay. uh, why I have put this thing is, you can see that here the formula is gamma g plus sc by 1 plus w. The same bulk unit weight, here they have given g gamma w into 1 plus w by 1 plus c in a different format. Okay, that's just because this sc, you can see you have sc instead of se, if you substitute wg here. Okay, g plus wg by 1 plus e into gamma w. This is gamma bulk. Okay, so instead of sc, if you substitute wg, you can take that g outside, so g gamma w by 1 plus w. I usually remember this formula because it's like a rhyming: g gamma w into 1 plus w by 1 plus e. Okay, in a dry soil, w will be 0, so if I put 0, so gamma d will become g gamma w by 1 plus e. Okay, and again, if you are going to have a fully saturated soil, so sre equal to wg, so your s will become 1, so you can substitute here, in terms of e you can substitute and get this formula: g plus e by 1 plus e into gamma w. Okay, from the one formula you can get all other formula. Okay, fine. And this one, gamma d equal to gamma b by 1 plus w, this is gamma b bulk. This is also one important formula: gamma d equal to gamma b by 1 plus w. This also derivated, derived from the previous formula. So you can actually memorize some formula like this so that it will be easy for you. Okay, now we'll move on to grain size analysis. Okay, can anyone tell me how many bones does a human have? How many bones do we have? A tough question, huh? How many bones? We'll just check how many are there. How many bones do we have? Any number, rough number? Okay, if I'm not wrong, I guess it is 206. Just correct me if I'm wrong. Okay, I didn't Google or anything. Just from memory, I'm saying 206, I believe. Okay. Why I'm saying is, see, in our human body, we have, it is important to um, differentiate. These are like thigh bones, and these are some ball and socket joints, everything we internally we segregate. Okay, similarly, when we take a soil, it is like an internal structure of the soil. Yeah. Yes, did anyone tell anything? Okay, so it is a internal structure of the soil which will help you to understand the behavior of soil. Grain size guys, if you want to tell me anything, yeah, you can unmute yourself, or else mute your microphone. Yes. So grain size analysis, as I said, it is like internal structure of the soil. Okay, where it is very important, when you where it is helpful in design of filters, even in filters in dams. Okay, we have in dams, we call it as filters, where we have to, in your downstreams, where you have to allow water to seep through the filter, or else the water pressure will be built up, but you should not allow soil to escape. So the filter material itself a granular material or a soil material, which will restrict soil, but whereas it will not restrict water. Yeah, I'll better mute everyone. Okay, so that no, it won't disturb my class. Okay, I have to. You can send me anything through messages. Okay, or at the end of the class, I will give permission to unmute yourself. Okay, it's kind of disturbing. Fine. So we are talking about grain size analysis. Okay, I'll just go through fast. Okay, so you can see this is a typical S curve for a grain size analysis. This is how you get. It is plotted between particle diameter in mm versus percentage. Okay, percentage fines, or call that as percentage of passing, which is in percentage, versus particle diameter. It is in a semi log graph. You have to be very much careful in this. For liquid limit and for grain size distribution, we go for a semi log graph. We don't go for a normal graph. Okay, many of the students, even here, if I take MTech class, people are forgetting that. Okay, only if you plot in a semi log graph, you'll be able to get the curve properly. So in a semi log graph, does anyone want to know what is a semi log graph? I hope everyone knows. If not, please let me know. Okay. So a semi-log graph will have a scale like this. You can see 0.001. This is 0.002, 0.003, in terms of in multiples of 10. 0.01, 0.02, 0.03, 0.04, 0.1, 0.2, 0.3, 0.4, 1, 2, 3, 4, 5, 6, 7. This is how the x-axis will be. Whereas the y-axis will be normal. Now, it's like just like in your normal graph. Uh, so the average representation of sizes of particles drawn on a semi-log graph for a diameter, particle diameter versus percentage finds. That is what we call it as grain size analysis. There are three sieving methods. One is dry sieve, wet sieve, and sedimentation analysis. I'll just tell you how this sieving or sieve analysis will be carried out first. For a soil, okay, I'm not talking about gravelly particle here. Okay, so when they bring the raw soil to the lab directly from the field, for which we have to perform the grain size analysis, we will take around 500 grams or 1000 grams of soil. It's up to us. Take 500 grams of soil, soak it in water for 24 hours. Then after 24 hours, take the soil, place a 75 micron sieve on a bucket. Okay, place a 75 micron sieve on a bucket and wash the soil on the 75 micron sieve very well. Okay, so the soil will be washed completely in a 75 micron sieve. And now, until you see a clear water, until you see clear water, the soil should be washed. Okay, so you'll be seeing muddy water coming below the fine. 75 micron sieve is like a cloth. Okay, very finer sieve it is. Then you will have clear water coming through the bottom. Then you can stop. You whatever retained on the 75 micron sieve, you use it for a coarser sieve analysis or dry sieve. Below 75 micron which have passed, that you have to leave it for settling for another 24 hours. Then once it settles after 24 hours, you take that fines that is in your bucket. Then you keep it in an oven. Now you have the fines that is kept in the oven. For that you have to conduct hydrometer. Okay, that is what is called as sedimentation analysis. So above 75 micron whatever retained, we will conduct dry sieve. Okay, this is the overall methodology that used to be followed for this grain size analysis. Do you want me to repeat? Is it clear? Take a soil, soak it in water, wash through 75 micron, whatever retained on 75 micron, keep it in oven and use it for dry sieve. Whatever passed through 75 micron, that also keep it in oven and keep it for sedimentation analysis. Okay, this is what sieve analysis will be initiated. Then you have to arrange your sieve. Generally from 4.75 we start. This is for coarser sieve, we stop at 4.75. uh, for sieving coarser fraction, we can start at 4.75, no issues. Okay, so you place your 4.75, 2.36, these are the set of sieves, standard sieves available. And bottom pan, you place it your sieves here and close the lid. You place your oven dried soil, that is retained. You have a retained, I will put some big particles here. Okay, this is our retained soil on 75 micron. Okay, I have oven dried, and now I am placing it in the top most sieve. Then it will be subjected to shaking. We will place this entire sieve set in a sieve shaker. It will be subjected to shaking. Then we will remove it. For after 5 minutes we will remove it. We will measure what is the weight of particles that is retained in each sieve. So at each sieve you will have some particles retained. You have to measure what is the weight. Okay, so that's how you will do. Once again you will get this graph. You have your set of sieves: 2.36, 1.18, 0.6, 0.425 mm, everything in mm. You measure what is the weight in each sieve retained. Okay, after performing shaking, you will do a sieve shaking. You measure what is the weight retained on each sieve. Find out what is the percentage. For example, your dry oven dried soil 90.83, that is what you are sieving. So 1.656 divided by 90.83. So you will get 1.82 percentage. Okay, so percentage retained is 1.656 divided by 90.83. You will get 1.82. Similarly, 6.397 divided by 90.83, 7.04. So you find out what is this percentage that is retained. Okay, then you find out what is cumulative percentage. Cumulative means you have to add. So the first value will be there, 1.82. Now 7.04 plus 1.82, that will give you 8.86. This you have to add. This value you have to add and you have to put it here horizontally. Add it and you have to put it here. So you will be having a cumulative percentage. Now you have to find out what is the percentage finer, which is nothing but 100 minus 100 minus 1.82, 100 minus 8.8, 100 minus 11. So you find out what is the percentage finer. Okay, this corrected percentage we generally will do when we go for cumulative plot, that we no need to worry now. Okay, this up to this is what important. So we find out what is the correct percentage finer. Now you have to plot a graph between your percentage finer and your sieve opening. Between percentage finer and sieve opening you have to plot a graph. That is what this graph. You will get a graph. There's some neat S curve most of the cases. Okay. Um, so when we get this S curve from a coarser fraction, we have to find out these three values: D60, D30, D10. See, somehow we need to classify the soil. We have to bring some parameters to classify for a broader classification, I'm saying. So even though we have sand, not all the throughout the world the sand is not going to be the same. Somewhere it is going to of uniform size, somewhere it will have intermediate larger particles and different sizes of particles in the sand. Okay, so when we have two different types of sand, how do I classify this is good sand, this is not a very good sand? How do I classify? So we have some terminologies called D60, D30, D10. D60 means 60, it corresponds to, for example, in from 60 percentage you have to draw a line it will hit a curve and you have to drop that on the x-axis. Similarly, D30 means from 30 percentage. Draw a line, hit the curve, and it has to be dropped in x-axis. D10 from 10 percentage. Draw a line, hit the curve, and it has to be brought to x-axis. D10 means 10 percentage of particles are finer than this size. That is, in that total amount of soil. Once again, my battery is running low. Yeah, thank you. So 10 percentage of particles, 10 percentage of particles are finer than this size. We'll get some sizes, for example, zero point 0.1 mm. We are getting a size, for example, zero point 0.2 mm we are getting. Okay, you are getting zero point 0.2 mm. That means that 10 percentage of particles are finer than zero point 0.2 mm. Here we are getting around some, how much? Okay, this is in points, in this scale. Okay, this is point 0.9. Okay, so zero point 0.9. Okay, one second. Okay. Mm, sorry for the inconvenience. Okay, fine. So 30 percentage of particles are finer than zero point 0.3. This is zero point 0.1, zero point 0.2. So it is zero point 0.3. So it gives you an idea of how the internal structure of the soil will be. Okay. See, there are some criteria for filter design. The filter design in a dam, they will give some guidelines like the ratio between your D60 by D30 should not be greater than 4. The ratio between your D30 by D10 should not be lesser than 1, something like that. The guidelines will be given. Okay, so only if we have some particular soil and we have a doubt whether the soil will be performing better for a filter design or not, how do we find out? So from the guideline we will be knowing what could be this value. We'll find the ratio and we will see. I told you the soil should be permeable for the water, but it should not be permeable for the soil particles itself to be taken away. Okay, so it should restrict the soil particles, but it should not restrict the water to flow through it. So only by knowing the size of particles and the range of D30, D60, D10, we'll be able to choose that material as a filter or not. Primarily, another one primary thing of use of this values are these values will help you to find out two parameters called as cu and cc, that is coefficient of uniformity and coefficient of curvature. These terms, they help you to classify the soil as well graded, poorly graded, or gap graded. We classify coarse grain soil only based on these two values. One is coefficient of uniformity, the another one is coefficient of curvature. So you can see that. So your coefficient of uniformity is nothing but D60 by D10, and your coefficient of curvature is D30 square by D10 into D60. So depending on the values or range of these values, we will be able to classify soil. For example, your Cu should be greater than 6 for a well graded sand, and your Cc should be between 1 to 3 for a sand to be classified as well graded. Well graded means it will have all particles in all percentages. so that they'll have a very good packing nature. If some particle size is missing, then there will be large voids will be created which should be filled that particle size only. If all the particle sizes are present in some equal proportion, it will form a very good network of closer or denser packing. Okay, so that's why they use these values to see how the packing of the soil will be. So in this d10 is called as effective size. This d10, you can use this d10 and find out the permeability even. So there is a relation between d10 and permeability k value. Okay, uh, so that's why this d10 is called as effective size, effective diameter. They call it as effective diameter, not d30 or d60. D10 as a direct relationship with your permeability is proportional to some constant or to the permeability. Okay, so because of that, this d10 as a very important it's a very important parameter to be measured. Fine, now you know how to plot the graph. Okay, how to do and how to plot the graph and how to take these values from the graph. So whatever I have talked is about only the coarser fraction that is retained on the sieve. Now we have some fines that has passed through the sieve. Water and fines has passed through the sieve. So for this fines, we have to conduct hydrometer analysis. I don't want to go much detail into hydrometer analysis, just giving a insight. Okay, so hydrometer analysis is carried out for the particles that is passing through your 75 micron sieve. Generally, silt and clay. To know how much percentage of silt and clay is present, we will conduct hydrometer analysis, which is based on Stokes law. That is, which relates the velocity, that is the terminal velocity of the particle to the size of the particle. It's like you put a very big ball and very small ball into the, when you drop it, because of the diameter, the bigger one will travel faster than the smaller one. Okay, something like that. So your terminal velocity is related to the diameter of the particle. So we are going to use that as a use parameter to find out the diameter of the particle in the soil. So this is your hydrometer. You can see it has a long stem and you have a bulb. Okay, so you have a bulb and a long stem. So you will have a 1000 ml jar. It will be your soil, your 75 grams passing through as oven dried. It is oven dried. Now you will take that soil, you will put it in a bowl. You will add sodium hexametaphosphate and sodium carbonate. To that you will pour water. These are called dispersive agents. Pour water, leave it for a day. The next day, mix it well. You have to take around 45 to 50 grams, not the entire fines that is collected. You have to take 45 to 50 grams of oven dried fines. Then you have to put it in dispersive agents, pour water, then you have to mix it well and make it as a 1000 ml. Shake it well. You have to do vigorous shaking of the jar, and then once you keep the jar, you have to put immediately your hydrometer. You have to put your hydrometer not like just dropping from the top. It's a very very sensitive. Okay, it will easily hit and get broken. So you have to drop carefully but fastly. Then you have to drop it. Then you have to start the timer. So you have to note down the time versus reading in the hydrometer. Then you will find out by using set of calculations and corrections like meniscus correction, dispersive correction, temperature correction. You will find out what is the effective diameter of the particle, and you'll know what is the time and percentage fines. The same graph, percentage fines and effective diameter, you'll be able to calculate. Okay, so what is the limitations of this test is, this test is applicable only for size range 0.002 mm to zero point 0.2 mm. Okay, this is very much important. Particle, the lower limit is 0.002 and the higher limit is zero point 0.2 mm. So bigger particles means it will have turbulence. Smaller particles means it will have Brownian movement. They say Brownian movement means it will keep on having some colloidal effect and it will affect the settlement. So this range you have to keep it in mind. Okay. Then the other things are much less important only, but this limitation they have asked in many question papers. Okay, see a we'll see a problem, a small problem which is similar to your assignment. So the CC value is 1, the CU value is 4. What would be the value of D30 by D10? This is one of the gate question also. They are asking what is the ratio of D30 by D10. Always start from the basic. We know CC is D30 square by D60 into D10, and we know CU is D60 by D10. Okay, they have put CC as 1. Okay, so CC substitute 1, which is going to be D30 square by D60 into D10. Now you equate. So D30 square is D60 into D10. You get a equation. Similarly, CU is 4. So D60 by D10 formula is equal to 4. So now you equate D60 is D time 10 times of 4 into D10. 4 times of D10. D60 is 4 times of D10. Now you substitute, we need everything in terms of D30 and D10. So you substitute this D60 in terms of D10, which is going to be 4. So D30 square equal to 4 into D10 into D10. So D30 is by D10 the whole square. This is 1 D10 square. Bring it to the down. You will get 4. So D30 by D10 is equal to 2. The same problem, the same method, you can use it for your assignment also. Okay, you start from the basic and then you can get it to the solution. Okay, fine. So we have come to the end of the session. Do anyone have doubts? Any doubts? Wait, I will just turn on the mics. Now you can, yes. Does anyone have doubt? Calculation for hydrometer, the tabular column, sir. Okay, sir. I didn't put it here, but because it involves once again, I didn't put it here, so it involves meniscus correction, dispersive correction, and you have to do a hydrometer calibration. It is little bit time taking process, but can I tell you, because I will put it in a detailed manner in a slide, so that with the help of slide I can tell you in next class. Can I tell you in next class, sir? It's a very detailed procedure if I have to start, because you have to calibrate the hydrometer first. You have to plot each reading from the center of the bulb at what height it is. Then you have to do. I will take a model calculation and I will prepare a table. Then I will tell you how each value has arrived, and I will explain you sure in the next class, sir. Thank you, sir. Yes, sir. Yes. Any other doubts? Uh, may I know for what reason? Okay, you have a discussion forum in NPTL. You can post it your queries in the discussion forum. Sure, I will see it and I will reply to it. You have a discussion forum, right? We have yes, you can ask anything in the discussion forum is encouraged. Okay, you can ask. You have a forum here. You can ask your question here. I will sure reply to it. And I'll also post this in the YouTube. Okay, that YouTube link will be shared. If you have any questions, you can share, you can post it in the YouTube comments also. I'll be answering it there. Yes. Yes, sir. SBC's, pardon, safe bearing capacity. Yeah, yes, please, you can you can post it in the I mean, you share your email ID in the what group. I will try to contact you, or you can share it in the YouTube question, YouTube video also as a comment. I can sure reply anything related or not related. Sure, I'll be happy to answer. Yes, sir. Yeah, thank you, sir. Assignment one, sir. It's already in the group, sir. I mean, it's already been posted. Assignment one is already there. Its due date is on 9th August. Yes, sir. As far as hydrometer is also concerned, that calculation, sir has also detailed, explained detailedly in this video. If it's needed immediately, means you can refer that lecture also, sir. In grain size analysis part two, he has discussed that detail. Even then, I will also explain in my next class, sir. Yes. Anything else, please? Any other doubts regarding grain size analysis? We have seen about water content, specific gravity, and grain size analysis. Okay, and field density. So all these four tests and methods we have seen. So if you have any doubt or clarifications or problems in the doubts, problems in the um, uh, what is that, by presentations, you have any doubts in that problems, you can ask me. The similar problems is there in your assignment also. The link for this presentation and video, everything will be posted in a drive. Okay, you can have access to the drive. No, sir, that we not use widely actually. Oil replacement method widely used in the field is this sand replacement method and core cutter only. We general Yeah, yeah, the other four methods, they have, I mean, they are not widely used, or it's like uh, they don't give much reliable results. The widely used is these two methods what we follow, and also in IS codes we have these two methods. There are also other methods for water content measurements also, but we generally use oven dry method. There is also calcium carbide method and other methods for oven dry. Just for knowing purpose, we have listed other methods. What we generally do in our lab or what we follow is this sand replacement and core cutter method. So soil processing is, sir, when we bring the raw soil from the field, we cannot directly conduct our test on those soil directly. So we have to air dry the soil, and we have to pulverize them, or we have to crush with a wooden hammer, and then we have to sieve it in a respective sieve whichever we require. For example, for compaction we require 2 sieve. So we have to sieve the soil through 2 and even though we break it with the clods, or I mean hammer or everything, there will be some bigger clods or something. So we will remove them, any roots, any other leaves, everything that we have to remove. All these process is called as soil processing. So before we conduct our test, before we start preparing our sample for the test, we have to perform soil processing, and we have to ensure that they are homogeneously mixed. So when we crush, each day we will crush some amount of soil. We cannot keep separately them. We have to mix all the processed soil together, so that they will have a homogeneous distribution of moisture content. So that we call the soil processing. No, no, not required, sir. We can conduct in our room temperature itself. We have to do a temperature correction then. That's what we have to report, that specific gravity at 27 degrees Celsius, which is a standard temperature. So we have to note down what is the specific gravity at room temperature. uh, yeah, we have to find out the room temperature, and we have to apply the correction factor, which is a standard. We have a standard table which will give you the relative density of water at 27 degree. uh, One second, I will just with different temperature we know what is the relative density of water. So with that we have to apply the correction ratio. uh, Yeah, yeah, at 27 degrees Celsius is what we have to report. I'll just share my screen once again. If you can see here, so we have a table like this. Can you see this, see, sir? Can you see my screen? Yeah. So you have a table like this. So we have to pick which is our temperature. For example, the temperature which I conducted was around 32 degrees Celsius. So it will, the value is 0.995. Okay. So divided by, at 27 degrees Celsius, it is going to be 0.995676. So we have to find what is the ratio. That is what here we have calculated. Yeah. In this table, you can see relative density at room temperature divided by relative density of water at 27 degrees Celsius. So at 27 degrees Celsius, you have to find out what is the relative density. That is going to be from this table. At your temperature, room temperature where you conducted, you have to know from the table. Then you find the ratio and multiply that with your value. You will get the specific gravity at 27 degrees Celsius. It's clear, sir? Yes. Tare means the cup. Cup. There what we use the containers we call sometimes tare, tare. In our weighing machine also we have a word as tare. In our weighing machine, if you know, tare means you make it zero. If you put if I, for example, I want to take some 50 grams of soil, I put a container or a tray on the weighing machine and I press tare, so it comes to zero. That is, the weight of the tray will be, it's not considered. So now I will take 50 grams. So tare, container are all the same. Yes, sir. Yes, any other doubts? Someone asked, yes, sir. Water content and SR, degree of saturation. So from the formula you need, or so from the formula, SR, degree of saturation, equal to water content into specific gravity divided by void ratio. SRE equal to WG, we call that as SR equal to WG by E. One second. So SR, that is degree of saturation, is nothing but water content into specific gravity divided by E, void ratio. These all derived from the three phase diagram. You can refer Gopal Ranjan. They have very well explained how these derivations have come. See, degree of saturation means, as I told, this much volume of voids, how much volume of water is present. That is what degree of saturation is. Yes, any other doubts? Pardon, sir. What happens if?